The EM algorithm is an iterative method that aims to find the MLE by enlarging the sample with unobserved latent variables. For example, for the two-component Gaussian distribution, we observe xi, and then we proposed a iterative algorithm where we try to utilize a latent variable zi, which indicate which component xi is from. We don't observe zi, we only observe xi. Suppose our data is x, and the log likelihood is this one, where theta would be a set of unknown parameters. Using the latent variable z, we can write the log likelihood as log of a sum. So for example, for the two-component Gaussian distribution, this summation is over all the zi's, taking value either 1 or 2. And then we have something like this. However, directly maximizing 3 is quite difficult due to the sum inside the log. So in the EM algorithm, we will pretend we knew z, and then we're going to work with the log of the joint likelihood. So it's log of this. Here, and throughout my later derivation, I will purposely keep my z in uppercase, indicating that z is a random variable because we don't really observe z. So each iteration of the EM algorithm involves 2 steps. In the first step, we take expectation. As I mentioned before, we wanted to work with log of the joint. However, we don't observe z. So we're going to start with some initial value. So we wanted to average over z. But how we compute the expectation of z? So we're going to find out the distribution of z, given, of course, the data, and also the current initial value of theta. So that's the E step. So let theta 0 denote the current value of theta. Then we first compute what is the conditional distribution of z given x and theta 0. For example, in the two-component Gaussian case, and that distribution can be factorized. They're independent for each of the zi, and we can compute what the probability of zi equal to 1 given the current parameter and also the xi. And we can do this, and we also compute the probability of zi equal to 2 for each of the I. And then once we find out the conditional distribution, then we take an average of the log of the joint distribution. Here, let's be a little bit careful. In this expression, x is the data given, and z is a random variable. We are actually taking expectations, so z will disappear. But the expectation depends on theta 0. But meanwhile, this log likelihood also depends on unknown parameter theta. So you have to keep theta. So this theta in red is not theta 0. Theta 0 only play a role in the expectation of z. So the whole thing is still a function of theta. Here, assuming theta 0, we already have the current value. So theta 0 is given. And this expectation, depending on z is continuous or discrete, will be either a sum or an integral. So we get our function g, and then we're going to find a value theta 1 that maximizes g. Then we're going to replace theta 0, the current value of theta, by the new value theta 1, and then just loop over and the EMF step until convergence.